have seen that using transactional memory could be a good idea, since it's relatively simple to insert the transactions. But the big question is, does it give us sufficient performance? And when IBM evaluated their Blue Gene hardware transactional memory, they compared using a standard benchmark from Stanford. And this benchmark is implemented with transactions, with OpenMP directives, and a single-threaded C++ code. Okay, and they compare it with single-thread execution, and that essentially only gives overhead, and with manually optimized OpenMP, and with a software transactional memory system where certain accesses to, namely to non-shared data, has been excluded from logging by manually marking these reads and writes. So that's a tedious process in my imagination, and well, I guess the simplest to do is to insert the transactions at suitable places. Okay, so I would like to make a remark. Sometimes one sees evaluations saying that something is 10% better than something else, and that's it. It could be interesting. Is something worth buying or producing or something else? But in reality, it's really much more interesting to see why we get the numbers that we get. And this is equally important for research papers, where this is a perfect example, and for master thesis. When one can read in an article or somewhere else that we saw something was some percent better for that, but we didn't have time to figure out, then at least my automatic translation is we couldn't figure out why. So that is not what to be written. We will see an example of how the IBM researchers at IBM Tokyo wrote when they couldn't figure out why, and it's quite nice description. Okay, but in general they explain things extremely seriously and in deep knowledge, as we will see, and that is obviously what is expected from probably the most the best research company in the world, in terms of, I mean, in the computer industry. They have most patents, at least. Okay, so what can we expect? Here are number of first level cache misses per 100 instructions. Okay, so for the sequential, this is basically the input to the machine. So this is running the sequential versions. Okay, and what can we see here? The short transactions, those which result in the cache block being removed from the first level cache at the store, they get more cache misses, L1 cache misses, and this is the long one, which invalidates the entire L1 cache at the start of the transaction. It is not that bad behavior, even if the entire L1 cache is invalidated. Okay, and here we can see the number of instructions. Instruction path length, that's the number of instructions executed. Okay, now we can see something funny, namely that for OpenMP, it was reduced compared to the sequential. And how can that happen? Well, they analyzed the code, the machine code, and found out that the reason was that the register allocator had done some different work. I mean, it had obviously produced some other code, and it more or less by chance, by luck, I mean, happened to use fewer registers that had to be, I mean, either reading or writing variables from memory, or saving and restoring registers at the beginning and end of a function. So this is not to say that there are fewer instructions always involved when we use OpenMP compared to not using OpenMP. Okay.